Right. We're going to study the logarithm, and before we do that, let's just do some uh, background study on the subject. So, if you remember, this is going back to familiar territory. This is the exponential. Okay. Now, this relationship can be expressed in another way, where y, the same entities, same quantities there that you see, is y log base b of x. All right, where b is called the base. All right. Now, before I get to what logs are good for and where are they used and why were they invented and so on, let's look at a couple of things. Let's look at a quick couple of examples. For instance, here's a quick one: log to the base 10, one of the most famous bases. Okay, one of them to the 10 is equal to 1. Okay, another one would be log to the base 10 of 100 is 2. Okay, and so on and so forth. All right, so there's just quick examples for you there. Um, Now what I want to do is quickly do the laws of logs, because once we do the laws of logs, then I can actually explain to you um, where did they come from and so on and so forth. Okay, so for any base b, there are three major laws, okay, that you need to know. They're called the laws of, I'm going to call them the laws. Okay, laws of logs. Okay, so the first law states that the log to the base b of x multiplied by y is log to the base b of x plus log to the base b of y. Okay, now this is all revision. This is not a first time on logs, but so it's more like a refresher. Remember, we're building up. This is a calculus kind of setup to get you up to speed with everything. So log to the base b of x minus log to the base b of y. So two of those, two laws there, and the third one, well, actually it's just these two laws, all right? And from these two laws you can derive a lot of things. For instance, the third, if we had log to the base b of x to the power y, okay, what is that? That is the log to the base b of x multiplied by multiplied by x multiplied by x multiplied by x. How many times? How many times are we multiplying here? Y times, okay? Y times. So that means that this is basically log to the base b of x plus log to the base b of x plus log to the base b of x. How many? Y. So that means that's equal to y log to the base b of x. Now this is usually considered a law itself, okay? So I'm going to put it down here as the third law because you should know it as a rule. It's quite commonly used, and it's a very useful algebraic tool to solve equations involving exponents, all right? Or exponential functions for that matter. So let me just write that down here for you. So if you had x to the y, that's the same as y log to the base b of x. All right, so those are the laws of logs, right? So here, let me give you a quick run through as to where logs were used. Okay, centuries ago, logs were invented by two different guys. In fact, at the same time, one was a Scotsman. His name was Napier. Okay, his name was John Napier, and the other was a Swiss mathematician by the name of Just Burgi. Okay, so both of them, they were published. Napier's results were or definition was published in 1614, and Burgi's logarithms came around 1620. So as you can see, this is not a new concept. It's quite an old idea. So anyway, during those years, during that time, it was rather difficult to do calculations involving multiplication and division. So what I mean is, example, 22.34 multiplied by 327.92. Suppose we want to multiply these two numbers. Let x equal this, and let's take the log to the base 10 of x of both sides base 10 of 22.34 times 327.92. Now that becomes, according to the law of logs, that becomes log to the base 10 of 22.34 plus log to the base 10 of 327.92. Further, it can be reduced. This is like 10 times 2 point, so it's log base 10 times 2.234. So I'm just going to say 2.234 plus log to the base 10 of 100 times 3.2792. Okay, and that comes to log to the base 10 of 10 is 1, log to the base 10 of 100 is 2, so that's like 3 plus log base 10 2.234 plus log to the base 10 3.2792. Now you just go look up a log table, and there you see the log table. Okay, so I don't want to spend, I'm not going to explain how to calculate it, but you can, it's very easy to calculate these logs. And then you just add the numbers, and then of course take the anti-logarithm, okay, which also comes from a table. So that was what logs were used for once upon a time. Nowadays, they're of course used for many other things. In addition to drawing, scientists, if you're an engineer or a scientist, you will eventually be using logs to draw graphs. They help put things in perspective. Log scales, they're called log scales. I won't get into details of this. The other thing which is very important in mathematics, and here, and why it's time to study logarithms, is because its relationship to the exponential function. Okay, so now I want to move on now to a special log. So the special log that I'm talking about is of course the log to the base e. Okay, so you've just seen log to the base b. Now we're going to look at log to the base e of x. All right, and it's much better known as ln, or the natural log ln of x. So this ln that you see here is the same as log to the base e. It's known as the natural log. I'm just going to write it short, natural log, okay? Natural log, and that's why it's ln for natural logarithm. Okay, so this ln that everybody seems to call this ln, but anyway, it's ln of x, and it's log to the base e of x. Now let's look at that relationship again. So you have, for instance, if we say y is equal to log to the base e of x, according to the definition, okay, according to the definition, that's the same as the relationship, which is x equals e to the y. Does that look familiar? Of course it does. That's the exponential function. So in fact, ln of x and e of x have a very powerful, a very important relationship. They are inverses of each other. So they are inverses of each other. So if you were to take e of ln x, that would be x. If you were to take ln of ex, it would be x. In other words, they both eradicate the effect of the other one. Now, since the ln is used more commonly, I'm going to show you a very useful formula, a very useful idea that can be used to convert bases. And what it says is that log to the base b of x, and I'm giving this without proof, is ln of x divided by ln of b. Okay, so you have log to any base b of x is equal to log ln x over ln b. The only condition here is that this is only for the case where b is greater than 0, okay, and b cannot be 1, for obvious reasons, because ln of 1 is 0. Log of 1 is 0. That's an important property. Actually, we should mention that. Let me just mention that here. The ln of 1 is in fact 0. Okay, that's an important property of the natural log. Okay, so b is greater than 0, b is not equal to 1, and of course x has to be greater than 0. These conditions have to hold for this rule to apply. Show you a quick example. For instance, if you wanted to calculate the log to the base 10 of 3, that would be the same as ln of 3 divided by ln of 10. Now, all scientific calculators have the ln key, the ln function in it, so you can actually just calculate log to the base 10 of 3 by using this simple conversion. Okay. Okay, now I'm going to do an algebraic example that uses the laws of logs. Now remember that the laws of logs also, same laws apply to the ln. It's not a different thing, it's the same entity. So I'll do a quick example, okay, that demonstrates how the laws can be used. For instance, if we had ln x cubed y4 divided by z to the 7, okay? And if we want to calculate the ln of this, the law of logs tells us that that's equal to ln x cubed, okay, plus ln y4 minus ln z to the 7, okay? That's the first thing we would be doing. And then, of course, we can split that we can reduce that further into 3 ln x plus 4 ln y minus 7 ln z. The last thing, one last point that may show up sometimes when we are studying calculus and ln, the log and exponentials, is the general exponential function a to the power x. Okay, a to the power x is really just equal to, we can write it as e ln of a to the x, okay, which is equal to, because you see e and ln, remember the exponential of the ln is just a of x, so it's just like 1 divided by 1 in a way. So that's by using the law of logs, though, I can bring the x down here, and that becomes e x ln a. So that's a useful little thing to keep in mind. Sometimes it may come in handy. Okay. All right, that's it for ln. Keep in mind that what's very important for you to realize is the relationship between ex and ln x. All right, they are from the same family. All right, they both work together. They are the inverses of each other, and that's the third reason and the current reason. Remember, we don't use logs anymore for calculations. We've got very powerful calculators. But so we don't use that calculation technique, the calculation example I showed you, but logs are now used for many other things. Like I said, log scale graphs are very useful, like using a microscope, like putting things in perspective, for instance, to see changes. But in mathematics, the natural log, not the log to other bases, but the natural log ln to the base e, is a very important function, because for one reason it is the inverse function of the exponential function, and the exponential function naturally occurs. It occurs in a lot of processes in nature. And remember again, I will remind you, functions are boxes, input, output. And what is the point of using that kind of analogy? It's not just an analogy, it's exactly what they are. That's how they work. Important thing to keep in mind, we're trying to model real life systems, and the exponential function is a naturally occurring function. Nature chose it, not us.